All right, this is going to be our walkthrough for the homework assignment titled Old AP Limits and Continuity. So most of these are just old AP questions. Some of them are multiple choice questions, which we will not have any multiple choice questions on the test, but that doesn't mean that these aren't still good practice for the exam. But some are multiple choice, some are free response questions, but they're all dealing with limits and continuity. So our first one here is just asking us which of these statements is false. So let's just look at each of them. The limit as x approaches 1 from the right exists. Well, here's 1, right? Here's x equals 1 on our graph. As we approach 1 from the right, yep, that limit exists, right? That limit is equal to, looks like this is 3 up here, right? So that one exists. The limit as x approaches 2 of f of x exists, right? As I approach 2 from both sides here, I'm approaching some number. I don't know what that number is, but it does equal some real number there, right? Both sides are approaching the same value. So that one exists. The limit as x approaches 3 exists. Well, from the left-hand side, we're approaching 1, and from the right-hand side, we're approaching 2. So this is false, right? Because the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. So this is our answer choice. Now, if we go through the next couple of them, at 4, as x approaches 4, that exists. Yeah, there's a hole there, right? But we're still approaching the same value. We're still approaching 4 as x approaches 4. And it doesn't matter that we have this extra point, right? That point isn't related to the limit at all, right? The value of the function doesn't have to be the same as the value of the limit. And at 5, yeah, they're both approaching whatever this number up here is. Looks like that number up there is 6. Right? As x approaches 5, this is equal to 6 as we approach from both sides. The corner doesn't affect anything. So that is our answer. For this one, we have the line y equals 3 is a horizontal asymptote to the graph of which of the following functions. So y equals 3 would be a horizontal asymptote when the limit as x approaches infinity of this function equals 3. And so we should know for rational functions like this one and this one and this one that we have to look at the degree of the numerator and the degree of the denominator. Now, we can write out the full limits, but if this was a multiple choice question, we wouldn't have to actually write out the limits. We would just circle the right answer choice. This one we can be certain is wrong. A linear function never has an asymptote. And this one, right, cosine of 3x, like if we think about the limit as x approaches infinity of this, the cosine of 3x is some number between -1 to 1 in the numerator, and in the denominator it's now infinity, which would be 0. So this one has y equals 0 as a horizontal asymptote. So it's not that one. And then all of the other 3, which will show the actual limit for the one that's the correct answer, but they all have the same degree in the numerator and the denominator. So the horizontal asymptote should just be the division of the leading coefficients. So in this time, it's 3 over -1. For this one, it's 1 over 3. And for this one, it's 12 over 4, which is 3. So the answer is D. Right? It's not any of these other ones. And if we wrote out the limit, it's important for us to know how to do this also. The limit as x approaches infinity of 12x squared minus 1, we divide every term by x squared to find this limit. But you'd have to show this work on my test, because my test isn't going to have a multiple choice question. So the limit as x approaches infinity of now, well, 12 minus 1 over x squared all over 1 over x squared plus 6 over x plus 4. And what happens is, as x goes to infinity, all of these things with the x's in the denominator all approach 0, and we just leave 12 over 4, which is 3. All right, for our next one here, we have a function that is continuous on the closed interval 3 to 7. And f of 3 equals 5, and f of 7 equals 25. We want to know what's guaranteed by the intermediate value theorem. Well, the only thing guaranteed by the intermediate value theorem is that every w between 25 and 5, or for every single one of these, for every w on that interval, there exists a c on the interval 3 to 7 such that f of c is equal to w. That's what the intermediate value theorem says. So basically, anything that doesn't have to do with the function equaling some value is immediately eliminated, right? Like attaining a minimum, that makes no sense with intermediate value theorem. F of x greater than 0, that makes no sense with intermediate value theorem. Now, f of x equaling 5 having a solution, that could make sense. F of x equaling 11 having a solution, that could make sense. And even maybe f of 5 equaling 15 makes sense. But it doesn't really, because f of 5 equaling 15, it just says that there is some number on C. It doesn't guarantee which number. So it's not going to be a specific x value that we're looking for here. So it's really either f of x equals 11 has a solution, or f of x equals 5. Well, f of x equals 11 is between 25 and 5, whereas 5 is not between 25 and 5. So the answer should be choice A, that 11, which is between 5 and 25, must have a solution between 3 and 7. All right, for this next one, we would note that when we plug in -3, we get 0 over 0. And so what we'll do is we'll just try and factor this. The limit as x approaches -3 of x plus 2 times x plus 3 over x plus 3 times x minus 3, right? Using a difference of squares in the denominator. The x plus 3's will cancel, giving us a limit as x approaches -3 of x plus 2 over x minus 3. Well, -3 plus 2 is just -1, and -3 minus 3 is -6. So we end up getting 1/6. For our next one here, we want to know for which of the following values of x is this function not continuous? Well, it's not continuous at anything that makes that denominator equal to 0, which would be x equals -2 and x equals 2. All right, so this is just going to be choice D. It's important, though, that like on my test, I'm going to ask you about classifying the types of discontinuities. Right? And so if I do a limit as x approaches 2 of f of x, well, that's going to be 2 times 2 is 4 in the numerator, times 1 times -1 all in the numerator, over something times 0, which is positive or negative infinity. So we would know that at x equals 2, it's an infinite discontinuity. Right? And at x equals -2, we'd first want to rewrite it as a limit as x approaches -2. We'd cancel out the x plus 2's, but we'd still be left with one of the x plus 2's in the denominator times the x minus 2. And so we'd end up with -2 minus 1, which is -3, times -2 minus 3, which is -5, over 0 times something, which is 0. And we'd again get positive or negative infinity. And x equals -2 would also be an infinite discontinuity. So just make sure you're able to classify those discontinuities using limits as well. All right, for number 6 here, we want to know which of these limits equals 0. Right? Well, all of these are x approaching infinity. And for every single one of those, e to the x is infinity, ln of x is infinity, x to the 100 is infinity, e to the x again is infinity, ln of x again is infinity, and x to the 99 is also infinity. So these are all indeterminate. So what we need to do is we need to determine which infinity is faster. And remember that our ordering for this is the fastest that we deal with is exponential, then polynomial, then root functions, which we don't seem to have any of, and then logarithmic functions. So in the first one, the infinity in the numerator is faster, which means this equals infinity. In the second one, the infinity in the denominator is faster, which means it equals 0. And the same with this one, the polynomial x to the 99th is faster than the log, so that one is also equal to 0. So it looks like 2 and 3 are equal to 0, which is answer choice A. All right, for this one, we need to recognize that as x approaches 7 from the left, x is less than 7. And the reason this matters is because we need to clear off the absolute value, right? And the only way to clear that off is to determine if the thing inside the absolute value is positive or negative. Well, if x is less than 7, then x minus 7 is less than 0, which means that the absolute value of x minus 7 is the absolute value of a negative value. And if it's the absolute value of a negative value, then to take its absolute value, we have to take the opposite of it. So what we have is now a limit as x approaches 7 from the left of the opposite of x minus 7 over x minus 7. And of course, the x minus 7s will cancel, and we just get the limit as x approaches 7 from the left of -1. And the limit of a constant is the constant. So we get choice B. For number 8, we want to figure out which of these things is a horizontal asymptote. So again, this is just a limit as x approaches infinity here. Now, in order to actually evaluate this limit, let's distribute out the function. So 3x times -2x is going to be -6x squared. And then 3x times 1 and -2x times 2 gives us a -x. And then we have a plus 2. And then it's all over, that's just a perfect square trinomial, right? So 9x squared plus 2 times 3 times 4, 24x plus 16. And so now the highest degree is x squared. So we'll just divide everything by x squared. And I know if this was a multiple choice question, you would just divide those leading coefficients, right? And we get -6 over 9, which is -2/3. But on my test, I want to see you actually do the limit. So this becomes a limit as x approaches infinity of -6 minus 1 over x plus 2 over x squared over 9 plus 24 over x plus 16 over x squared. And the whole reason why those leading coefficients are all that matters is because now each of these terms are going to 0, and we're just left with -6 over 9, which, as we said a minute ago, is -2 over 3. All right, this is similar to the one where we had the 3 different functions. Both x to the 5th and e to the 5x approach infinity as x goes towards infinity. But the exponential function is faster, and if the bottom of a fraction is getting bigger faster than the top of the fraction is, as they both go to infinity, it should be approaching 0. All right, for number 10, we're again looking at another graph and doing some limits graphically. So we have the limit as x approaches 6 of f of x equals f of 6. It says which of the following are true. So is that true? Well, the limit as x approaches 6 appears to be 4, right? Those values are going towards 4, but f of 6 is 1. Now 4 does not equal 1, so 1 is not true. So we can eliminate anything that has a 1 in it, which leaves us with choice B as our only possible answer. But let's go through 2 and 3 here to just see why they're true. The limit as x approaches 2 from the right of f of x is equal to f of 2, right? So as we approach 2 from the right, that's equal to -2. And f of 2 is the point up here, which is 3. Well, those aren't true. Those aren't equal to each other, so that's not true. And then for 3, the limit as x approaches 6 from the left equals the limit as x approaches 6 from the right. Well, yeah, from the left, it's approaching 4, and from the right, it's approaching 4, right? 4 equals 4. That's true. So that's why it was choice B. All right, here we're looking at a limit as x approaches infinity and negative infinity of e to the x times 2x squared minus x minus 3. So to do the limit as x approaches infinity, well, e to the x, or e to the infinity, would just be infinity. And 2x squared minus x minus 3, the 2x squared dominates that, right? And you can see that if you want, just like we kind of did with the polynomial, the rational functions, we can factor out an x squared, which gives us 2 minus 1 over x minus 3 over x squared. And as x goes to infinity, it's just infinity squared times 2 minus 0 minus 0, right? Which is just infinity. So it's infinity times infinity, which is just infinity. But for the second one, we end up with a limit as x approaches negative infinity gives us e to the negative infinity times 2 times negative infinity squared. Right? And the other two terms are just insignificantly small, just like we showed over here, like a 0. So we have infinity squared over e to the infinity. And just like some of the other ones we've dealt with, yes, these are both infinity, but the one in the denominator is faster, which means that this is approaching 0. All right, for number 12 here, we have this piecewise defined function g of x. And we want to know if g of x is continuous at x equals negative 3. And we want to use the definition of continuity to explain our answer. So first of all, the definition of continuity says that g of negative 3 has to exist. Well, that means I need to plug it in where the x values are allowed to be negative 3. So that'd be into root 25 minus x squared. So that'd be the square root of 25 minus negative 3 squared, or the square root of 25 minus 9. Well, 25 minus 9 is just 16, so that's 4. So g of negative 3 definitely exists. Then we need the limit to exist as x approaches negative 3. And the limit as x approaches negative 3 of g of x can only exist if the limit as x approaches negative 3 from the left equals the limit as x approaches negative 3 from the right. So we need to find those two limits. As x approaches negative 3 from the left, we just end up using that same thing. That's the square root of 25 minus 9. And we need that to equal the limit as x approaches negative 3 from the right, which will be the other piece, negative 3 plus 7. So we just get 4 equals 4. So the limit exists, and that limit is equal to 4. And so we can now say that g of negative 3 equals the limit as x approaches negative 3 of g of x. So yes, it is continuous at x equals negative 3. All right, for our next one here, same idea as the previous rational functions as x approached infinity. We're just going to divide by the highest degree here. In fact, actually, for this one, we'll show slightly different technique. What we'll do is we'll factor out that highest degree for both of them. All right, so same idea, but we'll just factor it out. So we have x cubed times 1 minus 2 over x, and then plus 3 over x squared minus 4 over x cubed. Right? As if I distribute that x cubed back through, I'll still get x cubed minus 2x squared plus 3x minus 4. And then in the bottom, we're still going to have the x cubed that we factor out. And in the bottom, we have 4, right, minus a 3 over x plus a 2 over x squared minus a 1 over x cubed. And so we can see then that the x cubes should cancel. Right? X cubed over x cubed can cancel out. And so we end up with a limit as x approaches infinity of 1 minus 2 over x plus 3 over x squared minus 4 over x cubed over 4 minus 3 over x plus 2 over x squared minus 1 over x cubed. As x goes to infinity, all these terms with x or x squared or x cubed in the denominators go towards 0, and we're just left with 1/4. And of course, if this was a multiple choice question on the AP test, you would just look at the fact that the highest degrees are 3 in both the numerator and denominator and divide the leading coefficients. But on my test, I want to see some work to show what that limit actually is. All right, for number 14, the horizontal line y equals 2 is an asymptote for the graph of f. Which statement must be true? Well, what does it mean to be a horizontal asymptote? It means that either the limit as x approaches infinity, well, actually, since it's x greater than 0, I was going to say infinity or negative infinity, but for x greater than or equal to 0, it would be positive infinity of f of x needs to equal 2. That is exactly what the definition of a horizontal asymptote is. And so we can immediately just go in and look. I mean, that's one of our answer choices, choice E. And so we're done there. There's no other option. All right, for number 15, we've got f is this piecewise function, and we want to know is f continuous at 3. So this is similar to one we did a little bit ago. If f is continuous at 3, then f of 3 needs to exist. Right? F of 3 is just the piece where 3 is included in the domain of that piecewise. So that'll be the square root of 3 plus 1, which is the square root of 4, which would be 2. And we also need the limit to exist, and the limit as x approaches 3 of f of x can only exist if the limit as x approaches 3 from the left of f is equal to the limit as x approaches 3 from the right of f. And so we need to see if that's true. So as we approach 3 from the left, well, that's the square root of 3 plus 1. And from the right, that's just 5 minus 3. Well, both of those are 2, which tells us that this limit does exist. And since the value of the function is 2 and the value of the limit is 2, we can say the limit as x approaches 3 of f of x is equal to f of 3. So yes, the function is continuous at x equals 3. All right, for this next one, we've got the function f of x equals 2x times e to the 2x. And we want to find the limit as x approaches infinity. Well, that's just infinity for the 2x, right? 2 times infinity is infinity. And e to the infinity is just infinity. Infinity times infinity is infinity. But as x approaches negative infinity, we end up with 2 times infinity times e to the negative infinity, which we know is infinity over e to the infinity, or we'll say 2 times infinity still, which is just an infinite number over an infinite number. But the exponential goes faster, and therefore this limit is 0. So you gotta be extra careful with those ones that involve the exponential functions. They'll often have a horizontal asymptote in one direction, but not in the other direction. All right, our last one here for this assignment. We've got a function, the absolute value of x minus 1 plus 2 when x is less than 1, and ax squared plus bx when x is greater than or equal to 1, where a and b are constants. So it says if a is 2 and b is 3, is f continuous for all x? So for part A of this, right, we are now looking at a new function, f of x is equal to the absolute value of x minus 1 plus 2, if x is less than 1. And we're looking at if a is 2, that'd be 2x squared, and if b is 3 plus 3x, if x is greater than or equal to 1. So for part A, we just have to see if this function is continuous, which means does the limit as x approaches 1 from the left equal the limit as x approaches 1 from the right? So for part A, does the limit as x approaches 1 from the left of f of x equal it from the right? Well, from the left, it's the absolute value of 1 minus 1 plus 2, which is 2. And then it's the limit as x approaches 1 from the right of f of x, which is 2 times 1 squared plus 3 times 1, which equals 5. And, well, quite obviously, 2 does not equal 5, right? And so, no, this function is not continuous. Okay? So the answer is no. Right? And our justification is that these two limits, the limit from the left and the limit from the right, do not equal each other. Okay? And then for part B, it says to describe all values of a and b for which f is continuous. Okay? And so in order to do that, we need these limits to equal each other. And we're no longer using 2 for A and 3 for B. We have our limit as x approaches 1 from the left, right? This limit is just 2. So we need 2 to equal the limit as x approaches 1 from the right of f of x, which is now equal to just A plus B. And so the answer to this question is all values of A and B are the values of A and B such that A plus B is equal to 2. So if A plus B equals 2, then f should be a continuous function. And we'll note that A plus B in part A, right, was 5, and that's why it wasn't continuous. And that is the end of our walkthrough for the old AP limits and continuity homework assignment.